All right, welcome to a podcast here on entropy and free energy. And kind of the big picture here is we're going to use this new concept of entropy and free energy, and also what we know about enthalpy to help us determine if we're going to have a spontaneous reaction or a non-spontaneous reaction. We're just going to call that reaction tendency. So let's start with what we know about delta H. Here we have a picture of a negative delta H reaction, an exothermic reaction. And I want you to think about this little hill of potential energy as if we had a ball on a hill. So it has high potential energy. And if I just gave that ball a little nudge on the top of the hill and it started rolling down the hill, it's going to do that all by itself, right? Spontaneously. Once I get it going, it is going to continue without outside influence. That's what I mean by spontaneous. And it turns out that if you have an exothermic process, if you can get it started, typically what will happen is it will continue without outside influence. Think about the last time you lit a Bunsen burner. Right? You took the match, you got that little spark inside of the methane stream, and the methane started to react with the oxygen, and the Bunsen burner stays lit until you turn off the gas. You didn't have to keep lighting matches to keep that Bunsen burner lit continuously. Once the reaction began, it continued without outside influence. It is spontaneous. On the opposite side of things here, imagine that we have a ball at the bottom of this hill. Right? This is the potential energy diagram for an endothermic process. If I try to get this reaction started the same way, just give that ball a little nudge, well, the ball doesn't go very far if I just give it a little nudge. And maybe it moved a little bit too much for the amount of force that we could imagine giving it. Regardless, it didn't go all the way up the hill. Right? If we wanted that ball to make it all the way up to the top of that potential energy hill, we'd have to continue pushing it, or in terms of chemicals, we would have to continue to input energy into that system to arrive at the energy of the product. So it takes a constant input of energy, so therefore we don't consider this spontaneous. This process it does not happen spontaneously. All right. Let me pose a question to you. Little ice cube over there. All right. Solid turning into liquid. We know already that the delta H of this process is about a positive 6 kilojoules. From what I just said, this should not happen spontaneously. Now I know what you're thinking. You're thinking something about it being hot and therefore it's going to get that energy. Well, don't think about that just yet, but that's a good thought. Just from a straightforward delta H perspective, we would not expect this phase change to be spontaneous. All right. So let's move on just a little bit, and we'll revisit that in just a second. There's another element that we have to think about here, and I probably shouldn't say element because this is chemistry. There's another phenomenon that we should consider, and that is this tendency in nature for ordered systems to become disordered. Right? We call it entropy, and kind of a non-chemical example that you might be able to understand is if I have a brand new deck of cards and it's ordered perfectly, aces to deuces, all 4 suits, and I start shuffling those cards are going to get disordered. Right? There's a very, 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 very small chance that if I keep shuffling those, they're going to go back into that original order. It could happen, but it's probably not going to happen if you're in your lifetime if you sit there and keep shuffling those cards. So there's this natural tendency towards disorder. This is just a cartoon that I like. Thank you, Mr. Harris. So let's think about this disorderliness, entropy, and state. Hopefully you can look here at the solid versus liquid versus gas and see that the solid has this really nice ordered crystalline structure to it. So this is probably some kind of ionic material that has its most order in the solid state. As we give it more energy, and now those particles can start to move a little bit and become liquids, right? They can move around and end up a little bit more disordered. They have a higher entropy in the liquid state than they do in the solid. And we end up with gases here. Once we give them so much energy that they completely overcome the intermolecular attractions between those particles, then they just float around within the volume of their container. So as we go from solid to liquid, or liquid to gas, we have an increase in disorder, and we have a positive change in our entropy, right? More disorder. So let's go back here. Think about our water. We have a solid turning into a liquid. We actually have a change here that is favored, right? We're going from a very ordered system to one that is less ordered, right? So that helps influence whether or not this process will occur spontaneously. Let's think here for a second about this chemical reaction. If we have liquid water that is going to decompose into, in fact, let's just say it's water vapor so that we don't have to worry about states of matter. So we have water vapor, two particles, two molecules there that we're going to decompose. And we're going to decompose them into hydrogen gas and oxygen gas. If we start with two molecules and we make three being a greater number than 2 means that our matter is now less organized. There's more disorder when we have 3 particles out of our 6 atoms than when we had 2 particles out of our 6 atoms. So that's one thing that we can look at as well. So we can look at the state of matter, and we can also look at what's happening with the particle count in the course of a chemical reaction to help us figure out what's going on with the disorderliness. It also turns out, and this you might find this hard to believe, disorder can be measured and quantified. So in the last podcast, you learned how to use the delta H from a table of heat of formations to solve for the heat of a reaction. Right? We took the sum of the product delta H's and subtracted the sum of the reactant delta H's. Well, I can give you a table of values for standard entropies, and we can calculate the entropy change of a system and figure out if it's going to be positive or negative, and therefore if it would tend to be spontaneous or not. So for instance, let's just look at the formation of nitrogen dioxide from nitrogen monoxide and oxygen. So what we can do is, first of all, we have to realize that when we're looking at our table here of our standard entropies, that we no longer have the assumption that an element in its standard state has a value of 0, right? That's good for delta H's, but for delta S's, our elements have numbers. So don't overlook that fact, right? Make sure you look through the table and get a number for each substance. But once we understand that, we can just look in the table and we can see that for our nitrogen monoxide, right? Nitrogen monoxide, it's 210.6 joules per Kelvin per mole. And since we have a coefficient of 2 there, we have to multiply our molar value by 2. Oxygen, we have 1 mole of that, so we just drop down the 205 from the table. And nitrogen dioxide is 240.5. And again, we have to keep in mind that it's 2 moles, so we have to multiply the molar value by 2. And we just apply our equation where the sum of the product entropies minus the sum of the reactant entropies, in this case, gives us negative 145.2 joules per Kelvin mole whenever we subtract them. All right, so this gives us a negative entropy, and a negative entropy means that we are going to have more order. And in fact, that's what we'd expect looking at this equation, right? Because we have gas going to gas going to gas, so we can't really draw any conclusions there about the entropy. But we have 2 particles of nitrogen monoxide, 1 particle of oxygen. That's 3 molecules that are turning into 2 molecules. So the decrease in the molecule count would lead us to believe this is not spontaneous, and it's verified here by the negative entropy. So from what we know about enthalpy and what we know about entropy, can we say for sure that we have a spontaneous process? Well, we said that a negative enthalpy and a positive entropy should be spontaneous, so guess what? If both of those conditions are true, we will always have a spontaneous process. The opposite is true. If we have a positive enthalpy and a negative entropy, it is never going to be spontaneous. We're always going to have some input of energy to get this process to occur. Then we have the conflicting scenarios. If we have a negative enthalpy, that should give us a spontaneous process, but if we couple that with an increase in the order, right, or a decrease in the disorder, which is unfavored, we're not sure. Same thing with positive enthalpy and positive entropy. They are kind of competing interests here, so sometimes they'll be spontaneous. Great. That brings us back to our scenario here with the ice cube that's going to melt. We have a positive delta H, which is unfavorable for a spontaneous process, but we have a positive delta S, which is favorable. So what must there be here to help separate things. And I think you've probably, since the first time you saw the ice cube question, been screaming at the computer, temperature, temperature, temperature. I know that if this system is at 0 degrees Celsius and above, or I should rather say above 0 degrees Celsius, we're going to see this thing melt. Or if it's below 0 degrees Celsius, now it's not going to melt. So temperature definitely plays a role. And what we can do is we can bring together, now that we have the three components for spontaneity, we can bring together our delta H, we can bring together our T, and we can bring together our delta S, and put them into an equation that is going to be kind of the end-all. Right? If we plug these things in and we do this calculation, we're going to be able to figure out if we have a spontaneous process or not. So let's kind of go back and expand on our chart. We've already said that if it's a negative enthalpy and a positive entropy, it'll always be spontaneous. So let's consider here, if we plug in a negative delta H and we plug in a positive delta S, but according to the equation it's negative minus a positive, that will always give us a negative value for our delta G. So whenever we start plugging in numbers here to our delta G, if delta G gives us a negative number, that means that it's always spontaneous. Right? We could do the same thing. If I have a positive delta H minus a negative delta S, that means a positive delta G will give us never spontaneous. And guess what? Back to our conflicting scenarios here. Not quite sure here, but with this equation, now we know that whether or not a negative negative or a positive positive is going to be spontaneous, that's going to depend on the temperature of the system. All right? So here's the thing, and we can look at this screen and determine this. The higher the temperature goes, right, what's going to happen to our ice cube? The higher the temperature goes, we are going to see the melting occur, right? And the higher temperature means this is spontaneous. Well, let's look at what happens here. If we have a really big T, right, a really big T will make our delta S more important, right? So it's going to be multiplied by a bigger number, which means we're going to be subtracting by that bigger number, so that gives us a negative number. Now, that is opposed to having a really low temperature. Low temperature here, the melting is non-spontaneous, just as you've already probably said a couple times out loud. That means this is going to be an itty bitty T, right? Very tiny temperature, which makes delta S really, that makes this very, very small and unimportant compared to the delta H. So delta H was originally positive. This part pretty much can go away to nothing if we have a small enough temperature. So that means our delta G will be positive. So at low temperatures, delta H pretty much determines the spontaneity. At very high temperatures, then the delta S gets more important, and that can have a greater influence on spontaneity. So let's just look at how we would use this. Determine the following reaction is spontaneous at 200 degrees Celsius, given that the delta H of the reaction is negative 113 kilojoules, and the delta S of the reaction is negative 116 joules per Kelvin. And there's two things here that I want to make sure that you're aware of. Number one, the delta H's are typically given to you in kilojoules, and the delta S's are typically given to you in joules. We can't do any math with these until we have the same unit. So let's just change I forget what I changed. Looks like I changed everything to kilojoules here. So let's make this negative 0.166 kilojoules per Kelvin. And that's actually the other thing I want to make sure that you're aware of is because the unit for entropy is in kelvins, we need to make sure that any temperature data that we're given, like this 200 degrees Celsius, also gets converted to Kelvin. And hopefully from gas laws you recall that we just add 273 to a Celsius temperature to give us a Kelvin temperature. So delta G being equal to delta H minus T delta S. All right, we can plug in our delta H, subtract from that temperature times our entropy value. And here we have negative 34.5 kilojoules. And what do we know about this? Negative means spontaneous. That's right. Guess what? Just like we could look at a table of values for heats of formation and come up with delta H, and we could look at a table of standard entropies, coming up, calculating the standard entropy change for a reaction, we can also calculate the standard free energy. And there's tables of values for this. So we're back to an assumption, though, that the standard free energy of an elemental substance is 0, just like delta H of an elemental substance in its standard state is 0. It's just that delta S that you've got to watch out for. So here's a table that you might see and a reaction that you might be able to look up. Is the following reaction spontaneous at standard conditions? Well, we're just going to look into the table. The standard free energy of calcium carbonate solid is negative 1,127.7. We'll plug in the others, and we are going to sum each side and subtract the products minus the reactants. So we kind of flip those over, and we're subtracting a negative value, so that becomes a positive. And we end up here with a positive 129.1 kilojoules per mole. And being positive, that means this is going to be a non-spontaneous process, which is good. Calcium carbonate, you might know, is limestone rock. Calcium carbonate, it's also the stuff that the shells of a lot of sea creatures are made out of. It's also the stuff that chalkboard chalk is made out of. And we don't necessarily expect to spontaneously have the chalk in my hand start to turn into carbon dioxide gas and disappear, right? Or those poor sea creatures just disintegrating into nothing, or virtually nothing. Calcium oxide, which would react with the water to form calcium hydroxide, which will go into solution, and then carbon dioxide gas. Those poor critters would have no homes anymore. So thankfully, it's a non-spontaneous process. Well, all right.